Thank you for introduction, and I thank you for invitation. I'm very grateful to participate in this conference. I wouldn't speak about toric actions exactly, but I will speak about actions on tori and some constructions which lead to nice geometrical objects. The main goal of this talk is to discuss the open question about formality of manifolds with special holonomy. So since I'm speaking in topological audience, I first remind some notions about the holonomy of Riemannian manifolds. Yeah, that's how we can. Yeah. This is actually two references of the articles. Both are available in archive. They were published 2 years ago in the Сборник of Mathematiический сборник or Сборник of Mathematics. The talk is mostly based on both articles, and I'm resuming. Let's take a connected Riemannian manifold. On the manifold, there is defined a parallel translation of vector fields along paths. So this is a, for instance, let's for a moment, let's take a point, fix it, and consider loops which start and end at P. For simplicity, we assume that this manifold is simply connected. The translation of tangent vectors at P along a loop determines the automorphism of the tangent space. And the deviation of this automorphism from the identity is described by the Riemannian curvature of the manifold. So if it's identical, the manifold is flat. So actually, this is the realization of the curvature on the manifold. So that's clearly, since we assume the parallel translation with respect to Levi-Civita connection, this automorphism preserves the inner product. We assume that manifold is simply connected, so it preserves the orientation. So the manifold is oriented at all. So the H gamma has to lie in the group S or D. All automorphisms of this type form a closed Lie subgroup, holonomy subgroup of MD, and up to conjugation, this group doesn't depend on the base points. So this is holonomy subgroup. In general, the holonomy group is just S or D. That's it. But there are very special cases. Then it could be smaller. There is the reclassification of such holonomy groups, which was done in the 1950s. It reads the following: if a simply connected Riemannian manifold is not locally symmetric, so that's the identity, so that's the Riemannian curvature tensor, it doesn't parallel, and the action of holonomy group is irreducible, in particular MD is not a product of two Riemannian manifolds, then its holonomy group belongs to the following list: SON, this is the most general situation; UN, in this case manifolds is 2n dimensional, and such manifolds are exactly Keller manifolds. These are also a definition because we can, there is a Keller metric on it, because we're speaking about its inner product in the tangent space, which is complex. This is a Hermitian inner product. SUN, this is a subcase of UN. It's and such manifolds are called Calabi-Yau manifolds. SPN, this is for 4n dimensional manifolds. And these are exactly hyperkeller manifolds. There is special action SPN, SP1 on 4n dimensional manifolds, and these are quaternionic Keller manifolds. How that looks like this action, how it differs from hyperkeller. So it acts by that. So we identify the tangent space with the n-dimensional quaternionic linear space, and the holonomy acts from the left by multiplication from SPN, and by the right by multiplication from SP1, from unit quaternion. Since the multiplication is not commutative, this is non-trivial action, it cannot be reduced to SPN. And there are two special cases: G2, which is realized only on 7-dimensional manifolds, and spin 7, which is realized only on 8-dimensional manifolds. These 6 groups, UN, SUN, SPN, SPN, SP1, G2, and SP7 are called special holonomy groups. And such manifolds with special holonomy attract a lot of interest from geometers for many reasons. I would like to mention that the original Berger list contained the subgroup spin 9, which is realized as a subgroup as SO6. But in the late of 60s, it was shown that with such a manifold has to be locally symmetric. It was independently proved by Dmitry Alexeyevsky and Brown, Gray. Since SPK, this is a symplectic group, k-dimensional, it lies in SU2K and it lies in U2K. The manifolds with SPN or SON are Keller manifolds also. These are particular cases, special cases of Keller manifolds. The most interesting property of these manifolds with this group SUN, SPN, G2 and spin 7 consist in the fact that the holonomy of such a type implies that the matrix satisfies Einstein equations in vacuum. So these manifolds are Ricci flat. It appears that until now, up to now, these are the only known examples of simply connected Ricci flat compact manifolds. If I would like to speak about non-simply connected, of course, there are examples of flat tori and the similar ones. But if I speak about simply connected, these are the only known examples. The interest in the string theory to the manifolds with special holonomy of dimensions 7 and 8 comes from the following fact. If dimension m is equal to 7 or 8, then M admits a non-trivial parallel spin of field if and only if its holonomy group is G2 or spin 7. So why it attracts special interest? And for the last probably 25 years, mainly that was discussed in literature related mostly to string theory. The explicit examples of Ricci flat matrix on these manifolds are unknown. It appears that it's easier, and that's how that was the existence of such matrix was obtained. It's easier to prove the existence of a matrix with such a holonomy on the manifold than to solve, to prove the existence of the solution of Ricci of this Einstein equation. So usually the proof consists in the following. We are proving that there exists a matrix with such a holonomy, and then we derive from it, from the fact that this holonomy implies the Ricci flatness, this matrix has to be Ricci flat. For G2 and spin 7, that was done by Bonan, the professor from France, the student of, former student of Berger, Marcel Berger in 60s. And for SUN and SPN, it was known before. So all known results concern only the existence of such matrix. The most famous one, the initial one, is the Yau theorem on Calabi-Yau manifolds. It establishes the existence of SUN matrix. Then generalized Kummer constructions by Joyce gave first examples of matrix on compact manifolds with G2 and spin 7 holonomy. It was in 95. First articles appears. And later another construction, and then its many ramifications were introduced. By original one was construction by Kovalov in 2003 by G2 manifolds. It's called the twisted connected sum. From the point of view of algebraic geometry, it's very involved, and so it needs to have a lot of information about the algebra geometric data coming into this construction. But for generalized Kummer construction, we can explain only in the language of topology of manifolds. So the compact Calabi-Yau manifolds are distinguished by the condition C1 equal 1. So the first chain class vanishes. That follows from Yau's theory. So what is the left cases except Keller manifolds? The quaternionic Keller manifolds. They are Einstein manifolds with non-trivial scalar curvature. All known examples of compact quaternionic Keller manifolds are locally symmetric. And for every simple group, there exists a symmetric quaternionic Keller manifold of positive scalar curvature. These are so-called Wolf spaces. They're actually, they're described in the book by Wolf of spaces of constant curvature. It's the person who introduced these spaces. There is conjecture by Lebrun and Salomon that Wolf spaces are exactly all complete quaternionic Keller manifolds of positive scalar curvature. And now we are coming to the last to the another point of view. So let's forget for a minute about holonomy for a second. Yeah, and remind what are the minimal models by Sullivan. Let's take a pre-graded commutative algebra over rationals with homogeneous generators, x1, x so. That's probably infinitely many, but such that all subspaces M1, M2 homogeneous subspaces are finite dimensional. We assume that an algebra is connected, so M0 is equal just rationals, and the multiplication by elements of M0 just the multiplication by elements from the rational field of coefficients. Such an algebra with a differential D, which is x from mi to mi plus 1 for all possible i's, is minimal if this is one of the definitions with this ordering of degrees, which is shown on the picture. It means that the differential xi is is expressed as a polynomial in terms of elements of lower degree. So this is the definition of minimality. And the minimal algebra is the minimal model of A if there is a homomorphism of differential graded algebras. I don't assume that A is minimal, it's just the algebra of this kind. And such that homomorphism, which induces an isomorphism of cohomology rings. So this is the minimal model. The next theorem says the following: for every compact cyclically connected manifolds or nil manifold X, the algebra of q-polynomial forms on X, there is a minimal algebra, Mx, and a homomorphism, which induces an isomorphism of cohomology. So that is unique, actually. They're unique up to isomorphic equivalence model of algebra of these q-polynomial forms. The algebra Mx determines the rational homotopy type of X, and in particular, the reducible elements are generators of the group hom p star X to Q, so the homomorphisms to Q. So a minimal algebra is called formal if there exists a homomorphism of this algebra to its cohomology rings with zero differential, which induces an isomorphism of cohomology rings. So this is in particular, this means the following: starting just with cohomology ring of the algebra, we can reconstruct the minimal algebra uniquely. If that's now there are formal spaces, that's probably the main point. A space is called formal if its minimal model is formal. So it's the minimal model of its cohomology ring. What I did say before about the reconstruction of the homotopy groups tensored by rationals means the following. So this is the rational homotopy type of X. It's just the minimal model X is the representative rational homotopy type of X, is reconstructed from the cohomology ring. So starting with cohomology ring, you can compute ranks of all homotopy groups in particular. You can get more information. There is another generalization which appears from the attempts to prove that some spaces are formal. A differential manifold is called geometrically formal if a product of harmonic forms is harmonic. This property implies formality. In particular, by this way, the formality is established for symmetric spaces. That's probably very clearly, very well explained in the book by Griffiths-Morgan on rational homotopy theory on its differential forms. And what are examples of formal spaces? Symmetric spaces, they are geometrically formal. So what does it mean? It means that in this case, we could just substitute to every cohomology class just its harmonic form which realizes its geometric class, and we get the kind of equivalence of cohomologies and this minimal and this and the space of differential forms. The K-symmetric spaces. This is a generalization of symmetric spaces, and that was established by Kochik and Terzic. The strategy is completely different from symmetric spaces. For symmetric spaces, there are two possible strategies. First, use these harmonic forms and derive it from geometric formality. And another strategy is derive it from the Cartan representation of the algebra of invariant forms on homogeneous space G over R. So this algebra, this invariant forms, gives you a minimal model of this space, and so we can compute. It can be computed from the data G and H from these groups, and we can derive it by algebraic means without using these analytical properties, without using harmonic forms. And so it was shown in particular by Kochik and Terzic that some case-symmetric spaces can be proved to be formal by using this Cartan approach, and by being not geometrically formal. The third example are closed simply connected manifolds of dimension less than or equal to 6. This could be a kind of explained that there are no obstructions to formality for these manifolds. They're too small for that. They have too small dimension. And the famous theorem is that's also which we have to mention. It's and which is the basic for our for the discussion is the theorem by Deligne, Griffiths, Morgan, Sullivan from the middle of 70s. One of the first articles about application of rational homotopy theory to differential manifolds, which states the Kähler manifolds are formal. There are two different strategies in this proof, analytic and also more or less algebraic complex analytic, which establishes, which gives this result. So we either have compact simply connected Kähler manifold, then it is formal, and so we can compute from its cohomology ring the ranks of all homotopy groups. So we can reconstruct the whole rational homotopy type completely. This conjecture led to some proposal that since the Kähler manifolds were the first examples of compact symplectic manifolds, and even until early of 70s, there were known other examples before Thurston didn't show that the product of the Heisenberg free manifold and the circle is a symplectic manifold, which is not Kähler. So that was conjecture that probably there are simply connected symplectic manifolds are formal. The conjecture is due to Lupton and Oprea, and they kind of formulated it on the brink of 80s and 90s. And in 1998, it was disproved by Ivan Babenko and myself in the article, which consists in the following. So that's the formality of non-formality of nil manifolds, which are different from tori. It's kind of easy to derive from the Cartan model of differential form on nil manifolds. So we took the Kodaira-Thurston manifold. So there is obstruction to formality, non-trivial massy products on this four-dimensional manifold. We embedded symplectically into CP5, CP6, or other manifolds of high dimension, and then take the symplectic blow up of this manifold. So they take fiberwise blow up of this manifold. We get the symplectic structure. This blow up was introduced by Gromov. And then by some algebraic tricks with chasing these non-trivial massy products in these exact sequences, we show that the non-trivial massy product persists, but probably in another dimension. But it leads to another non-trivial massy product, and so it's again the resulted manifold is not formal. So how that was proved by us from all simply connected manifolds from dimension up to from 10 up to for the lower dimensional case, 8-dimensional case that was established by Marisa Fernandez, her collaborators, a little bit later. So that's since all other symplectic manifolds are of dimension less than or equal to 6, so that covers all possible dimensions now. But you see the construction of simply connected symplectic manifolds. That's there are too many constructions with it. This is a very soft property. It's not that rigid as a Kähler property. So one couldn't expect usually. There were no reasons to expect these formality results, especially when it became known more and more constructions of symplectic manifolds. Topological constructions, more different, which are different from topological point of view. What is the obstruction? The obstruction are massy products. I shall describe it, this abstraction, this definition of massive products, how it appears. It first done in our article with Ivan Babenko in 2000, in 2001 probably. I don't remember when it was exactly published in the journal, the same journal, Sbornik of Mathematics, but in archive it was in 2000. So take alpha 1, alpha n homogeneous cohomology classes on the algebra M, and take their representatives A1, An. And consider the Maurer-Cortin equation. This is dA is equal minus A bar verge A. And this is the matrix at which all elements except the only one tau, which is then upper right angle, are trivial. And the A has to be of the following form. It has to be upper triangular, with zeros on the diagonal, and the elements A1, An, A2, An on the up diagonal. So on this line. Other elements could be any. So take all solutions of this equation for all possible representatives. So the A bar is obtained from A, then every entry is taken, for every entry we take its bar, and then bar is defined as A bar is equal minus 1 in the power k times A. There is A is k-dimensional element. The set of all solutions of these equations for all possible representatives of this class alpha and all possible other entries form the entupler massive product of the cohomology classes alpha, alpha n. So this is not just a massive product, it's not just one element, but it's the set of elements from the cohomology group. The simplest example, actually, originally, this representation was derived from the initial definition by Kranis. Probably initial was by Massey, but the first big article with all algebraic details and many facts were written by Kranis in the middle of '60s, just to make it easier to describe what are high massive products, just to use one blackboard to introduce them, just to simplify there. But it appears that such a representation has other nice features which could be applied to other problems. But usually, even in the books by Griffiths-Morgan, only the triple massive product is explained, because if you come to the previous picture, you see what is the triple massive product. For the solution of the Maurer-Cortin equation, we do need that the product of alpha n and alpha 2 vanishes. Also, the product of alpha 2, alpha 3, it also vanishes. Take the solution of these equations. Here has to be also du is equal alpha 1, alpha 2. Probably it has to be wedged here. And dv equal alpha 2, alpha 3. And then tau takes this form. Here the p and q are the degrees of these two elements, alpha 1, alpha 2. So just I add this minus in some power term before these brackets, just to fit with the previous definition from the Maurer-Cortin equation. But it's quite clear that already this element inside is non-trivial, or is a cocycle. You can just take it d of this element and see that it vanishes because of these two properties. So the massive product is trivial if it contains d0. So it's a lot of set, but if you just has a solution set that tau is 0, cohomologically, the cohomological class tau is 0, then they say that the trivial massive product vanishes. And there is the criterion for non-formality. There is no criterion, but okay, there is non-trivial massive product M, then M is not formal. Formality can be derived for is equivalent to other statement, but I wouldn't stay on that. So that's more, it will take some time. But I'm just looking for criteria for non-formality. So that's if you do have non-trivial triple massive product, then M is not formal. Usually that's how this is. In our case with Babenko, we are working with triple massive products, and how that we established the existence, the non-formality of these symplectic manifolds. And now the question arises, are compact simply connected manifolds with special holonomy groups formal. The reason, of course, it looks that no special reasons. The only, you see, that's Keller manifolds are formal due to Griffiths-Morgan-Sullivan theorem. Quaternion Keller manifolds, they are formal if the Lebrun-Solomon conjecture is true. And it's more people believe that it's true than it's wrong. Even there were some false proofs already appear to this conjecture, but there are some, it's difficult. The only case is G2 and spin 7. They're just on the brink of possible dimensions with manifolds could be non-formal, 7 and 8. And also, in difference with symplectic manifolds, the construction of non-trivial holonomy groups is very rigid. It's not that soft. So actually, there are there are two ways I already described. One is going to Kovalov construct, to Joyce construction. This is generalized Kummer construction, and this is a twisted connected sums and its generalizations. What could be possible obstructions to formality? Keeping in mind that the manifold assumed to be simply connected. So the first Betty number vanishes, fifth Betty number vanishes, in a sixth Betty number vanishes in 7-dimensional case. The only possibility would be the existence of non-trivial massive products of free elements of degree 2. And this product would be of degree 5. For spin 7, there are two possibilities: similar product of degree 5 and the product of elements of degree 2 to 3 of degree 6. So there are two possibilities for simply connected case. So in this case, if we would like to check this conjecture, probably for known examples, you have to chase for non-trivial triple massive products, because quadruple massive products have too large degree. And so the only abstractions can be in this massive products which I did mention. So now I'm coming to the Kummer construction, because it's topologically, and I should describe it without any use of algebraic geometry. And what's the Kummer construction? They take a 4-dimensional torus, take the involution, which maps x into minus x. So we think that's 2-dimensional torus. 4-dimensional torus is realized as R4 modulo some lattice of maximal rank. So the x is the kind of coordinate on the torus defined up to lattice points. It has 6 fixed points of the involution. This gives rise to 16 conics over RP3 points in this quotient T4 over Z2. By resolution of singularities, we replace these cones by fibrations over CP1 as 2 with fibers diffeomorphic to 2Ds. So we have actually RP3, we have to, topologically, we're forgetting for a second algebraic geometry, but this is algebra geometrical constructions. We remove this cone, we have the boundary RP3, and we replace it by the fibrations of CP1. So what it could be fibrations? One fibrations we do know. For instance, you take the S2, take all tangent vectors of length less than or equal to 1. This is 4-dimensional manifold, whose boundary is the manifold of unit eigenvector, unit tangent vectors, and this manifold is exactly RP3. So then they're gluing this such a thing. Actually, in this case, we have to work with cotangent bundle to respect all orientations. So that's, but speaking about the situation with tangent bundle of S2, we have the cycle S2, where it has self-intersection and index is equal to. What is it? Because 2 is the Poincare characteristic of 2-dimensional sphere. So it's just the early Poincare characteristic, early characteristic of 2-dimensional sphere is just exactly the index of self-intersection of the zero section of tangent bundle. So every copy of CP1 in this case is replaced by a 2-cycle Z with self-intersection equal to -2. It's because of the orientation. So we have 16 new generators of H2 over Q, all the rationals. And so we have projections of two tori. There are six generators of the group H2 of T4 with the following intersection form 0, 2, 2, 0. This is on the quotient. And in terms of these cycles, we have the intersection form of the Q as follows: 16 copies of -2 and 6 copies of 2H. This matrix. Therefore, the signature of the Kummer surface is equal to -16, and the second Bethe number is equal to 22. That we know. But of course, this intersection form is not unimodular. But over Z, it has to be unimodular. Now I would like to stop for a second to describe the limit of the reduction of Kummer construction, its version for T2, how it looks like for T2. So again, we take two-dimensional torus, take the anti-involution, x minus x. We have 4 fixed points, 4 conics, which would be conics over S1. RP1 is equal to S1. So the smoothen and then, and what will the resultant manifold after this Kummer construction? You will get a two-dimensional sphere. And this involution looks like the hyperelliptic involution of two-sheeted covering of a two-dimensional sphere by an elliptic complex curve. So this is the two-dimensional version of the Kummer construction. Four-dimensional version leads not to sphere, but to K3 surfaces. The notion of K3 surfaces appears at the later 50s. And before, just on the same year, then it was first time appeared in the literature, there was an article by Milner dedicated to the Rockwell theorem about signatures of spinor manifolds, four-dimensional manifolds. It was published in the proceedings of some conference in Mexico. And he proved the following: an even undetermined unimodular form, even it means that the scalar product of each element, the square of each element is divided by 2 over Z. So it's an even number. Undetermined unimodular form over Z, it has to be intersection form over Z for this surface, is uniquely defined by its rank R and the signature tau. So this is a theorem which is derived from the theory of lattices, from the number theory. So in this case, Milner relies on some articles from number theorem from 30s and even in some earlier. So in this case, E8 is the Cartan matrix for the group E8 with multiplied by -1, and the intersection form of K3 surface is equal to 2 copies of 8 minus 1 and 3 copies of H. So H is hyperbolic intersection 0, 1, 1, 0. Yes. So in all books on algebraic geometry, the description of the intersection ring for K3 surfaces is given with the reference to the Milner theorem. And it was funny, even the note in the article by Milner that he discussed the Rockwell theorem about signatures that has to be divisible by 16. In this case, it's clearly divisible by 16. He mentioned at the end, in the very last page of this short article, that just Hirzebruch had shown him this algebraic surface and proposed to compute the intersection form, to compute the signature of it. So he did it with intersection form and checked the Rockwell theorem and discussed the Rockwell theorem and some other results around it. Very nice, very interesting article. And I would like to mention that the manifold is even because it's a spin manifold. So this form, intersection form, has to be even. So the explicit construction of canonical basis, which is based only on this Kummer construction, was obtained by us in our first article when did this exercise without using the theory of lattices. we tried to look for such a construction. I looked in the book by Huybrechts about K3 surfaces, very recent book, 5 or 6 years ago published. And it was mentioned it's interesting to derive that. And we were looking for kind of the ways to compute intersection forms of G2 manifolds. So we did it using the root decomposition of E8. So that's done. Of course, there is another way. One can take the manifold for manifold, topological for manifold with such a form, construct the canonical basis, and then by Friedman theorem derive that it's topologically equivalent to K3 surface. That's another way, but the idea was to get it from this simple data, because that could be used in the other cases, in the case which we're interested. So now, from what was the idea to use it? There was the idea to compute the intersection form or intersection, okay, or cohomology product of G2 manifolds, because we were to check the non-triviality massive product. We have to obtain pairs of 2 cycles. Those products vanish. So we use the intersection form, which defined as follows. This is the definition. It's purely algebraic definition, where D is the Poincare duality operator. Actually, this definition is given only in terms of Poincare duality, but its geometric realization was widely used by Pontryagin. He called it the intersection ring of cohomology, intersection homology ring, even of homology. What was the idea? He took the k-dimensional cycle, took another l-dimensional cycle, intersect them, got the cycle of this dimension k plus l minus n, and say this is the result of this intersection. And then Poincare dual, it gives you that this is a dual to this product. So this geometric realization is due to Lefschetz. For the cycles of those, for the case k plus l equal n, that was exactly the Poincare duality. For algebraic cycles, Lefschetz proposed to do that. In this case, that's were no such difficulties of algebraic cycles to compute the intersections on algebraic manifolds. And also Lefschetz told that one can do that in general situation of manifolds, not algebraic manifolds, not even even dimensional, for general manifolds. And that was realized by Pontryagin. He even wrote the article together with Glazerman that carefully clarifies and confirms this construction of Lefschetz. It was published in the late 40s, and the English translation was published as a book in American Mathematical Society in the early 50s. Even in his article, he wrote that we have to be careful, so they have to introduce special simplicial decomposition of manifolds, very special one, for which we can derive then transversality of intersections, for which we can discuss the transversality of intersection that's necessary, then speaking of simplicial subcomplexes. And also he told another problem that it's unclear, is every cycle realized by submanifold? So that's also we have to work in more general situation. At this time, the Tom problem was not, the steering problem was not solved. Actually, the article by Pontryagin goes back to the early 40s, because it was diploma thesis of his student Glazerman, who finished it in 41 and then was killed on the war, on the Second World War. And only after the Second World War, Pontryagin, with the help of his other students, published this article with Glazerman, a joint article in Russian Mathematical Service. So we can do this intersection forms. We can do it just, we can realize cycles by kind of simplicial subcomplexes, took the intersections of submanifolds, and let's construct the intersection ring, homology ring. And the cohomology ring, which we just dual to it. And now I come into the example of the Joyce manifold. I have to be fast because I do have only 3 minutes. Okay. The take 7-dimensional torus, I consider on it 3 involutions, alpha, beta, gamma. This is the general picture, 3 involutions. These involutions pairwise commute. For simplicity, I'm taking the simplest example from Joyce, B1 equals C5 equals 0, B2 equals C1, C3 equals 1. So we get a resulted from this construction, we get a simply connected manifold M7. What is it? Gamma acts on the cohomology ring by involutions. H1, H2 doesn't have non-trivial invariant subspaces. H3 generated by 7 forms, invariant subspace by 7 forms. So this implies that B3 T7 over gamma is equal to 7. And since, okay, the volume form is gamma invariant, so we have also similar statement for 6, 5, and fifth Betti numbers. The action is not free. Every involution, alpha, beta, gamma, is similar to the Kummer involution. It's just involution. It has fixed points, but it consists of 16 three-dimensional tori. What is it? You see, it's gamma free and gamma over z x by non-trivial permutation of these point sets. So that's, and the products of different elementary involutions have no fixed points. For instance, take alpha. Alpha acts on the first 4 variables as the Kummer involution and it fixes 3 other variables. So it just what we get. We get as a result T3 times T4 over Z2, where T4 over Z2 is a singular Kummer surface, which we described when we spoke about the construction of K3 surfaces. So P1 is equal 0 because the singular surface is simply connected. The singular set splits into 12 free tori. What is it 12? Because it has 16. For instance, for alpha, it has 16 free tori. Beta and gamma takes by x by non-trivial permutations. To every alpha corresponds actually to in the fixed point set as survives kind of 4 free tori. But this is 4 just for every involution alpha, beta, gamma. 4 times 3, we get 12. We get 12 free tori. And for every single torus, there is a neighborhood gomomorphic to the T3 times the 4-dimensional disk quotient with respect to this Kummer involution. It's the exact this cone is in the Kummer construction. Exact the cone in 4-dimensional conic points, 4-dimensional conic points. And from topological point of view, M7 is constructed from T7 over gamma by fiber-wise resolution of singularities in D over Z2. And this construction is exactly which we described before in the Kummer, in the construction of Kummer surface. Only we have to do it fiber-wise. And the fibers are parameterized by 3-dimensional torus. That's all. And now, we see that we can get we consider only generators over Q. The rational homology groups of M7 have the following form. B2 is equal to 12, and the generators are given by 12 cycles C delta I corresponding to submanifolds of the form CP1, which appear after resolution of singularities at the fiber of one of these 12 fixed tori. B3 is 43, generators given by 7 toric cycles, which correspond to these invariant forms. This is 7 of them. And 36 free forms, which are just locally near this fixed tori, the products of CP1 and one of the generators, 1 cycles on a torus. For torus is 3 dimensions, so 3 generator cycles. We have 3 times 12, 36, and there is 43. So now we get this representation of all generators of rational homology groups. There is complemented generators of complemented dimension. And now we get the theorem. The rational homology groups have the following generators of dimension less than or equal 7. So this is a dimension 2, 3, 4, 5. I probably wouldn't. They're easily described in these terms. These are already described to you. This is a toric generators. This is just this is products of CP1 over S1. These are just a different CP1. Delta corresponds to involution and I to the number of the subtorus, to its number of this torus. And the non-trivial intersections you can compute easily because from topological construction. You can very easily to compute them. So that's for this construction is -2 for 8. Actually, this is the duality between this Poincare duality between homology groups of complemented dimension. And these are non-trivial intersections. C delta I is equal -2 T delta. So this is intersection, this gives you Torus, and another non-trivial intersection. So we can compute the intersection homology ring of this Joyce example. I'm coming to the remarks. For describing the cohomology ring, it's enough to correspond to every generator, the generator of complemented dimension. I called it A bar, and every relation A cap B equals C replaced by relation D A bar cap B bar equals C bar. So we reconstruct the cohomology product, what was important, because in the article by Joyce, the Betti numbers were computed, the cohomology, the ring structures were not computed, and the question, how do they look like, were remained open. The first line in theorem describes the pairing of the groups, which takes the form, I already mentioned that, and they show this slide. And another, the main idea was to catch non-trivial massive product. I didn't write down all these statements very carefully, but now from the construction of this cycle, it's quite clear that M7 has no non-trivial massive products. Although it's not kind of rigorously kind of stated in the theorem, but it's quite clear. It will take probably more time to derive it, but it's not interesting, because if it would be non-trivial, it would be some hint that there is non-trivial. That would be worth to find it and show that there are non-formal G2 manifolds. Joyce's example obtained by different construction, which split into 3 types. There are finitely many constructions, actually, finitely many of them, but they're split in 3 times. So it's I consider it only the simplest case. Then my students in their diploma works Fedorov and Todikov considered the case there are more complicated structure of fixed Torus, and Todikov there are more complicated structure of the fiber-wise. There's a D over not Z2 but ZK. The K is not D, but not 2-dimensional, but 3-dimensional disk, 3 complex dimensional disk over or finite groups. And they computed also for certain examples the intersection rings. It's okay, they're finitely many examples, so we don't want to check them one by one. But it's quite clear now, looking at these computations, that this Joyce example doesn't give you manifolds with non-trivial massive products. So that's, I don't want to prove the theorem very rigorously with long statements and consider all these more than 100 cases of examples. But it looks that all these manifolds are very similar to K3 surfaces. And further, not these analytical reasons as scalar manifolds, but some topological reasons, they are formal. So that's formality. So this attempt doesn't lead to the disproving this conjecture. Probably it's correct. Other constructions, they also based on algebraic geometry, the twisted connected sums, and probably one can also establish the formality of these manifolds. But still, the questions looks interesting, and I think it's application of this intersection form also could give some more data, give you a possibility to reconstruct the intersection form of these manifolds. Here I would like to stop. I'm sorry because I slightly over my time, not slightly over. Okay. I started 3 minutes later, so thank you for your attention.
Okay, let's unmute the microphones and thank the speaker.